All right, so let's look at number 8. This is from the self-test. So for this problem, there was about 71% of you guys that responded to this one. So this is the one that most people had a question on. So this is one of those where we're going to set up a table. So where it says tree diagram, we're not going to do that. But let's read the instructions here. It says, the Criminal Justice Department at a local university estimates that in 85% of the cases brought to trial in the country, or in the county court, the defendant is guilty. And that 10% of guilty defendants are found innocent, and 5% of innocent defendants are found guilty. So we're going to set up our table. So on the test, now when you guys took the quiz, I had these two pieces labeled for you, but on the test, they will not be. Okay, so you got to figure out what's going to go in those places. But it's pretty simple if you've been practicing these, which hopefully you have been. Remember up on top here, this is where we're going to put what's actually happening. So in this situation, people are going to court, and some of those people are going to court and they are guilty, and some of them are going to court and they're innocent. Okay, now they're not being found guilty or innocent yet. That's just what's actually happening. You're going to court, you're either guilty of the crime or whatever you did, or you're innocent. Okay, now then we have what's being decided. Maybe it's a judge or a jury. That's what's going to go over on this other side. So in this situation, we have that people could be found innocent or found guilty. Okay, now you could have those switched around if you wanted to. It doesn't matter. If you had those switched around where you have your numbers in the next or in the table, those will be obviously switched around as well. But in the long run, it shouldn't matter. But for this case of this, or for the sake of this problem, if you want to follow along, you can set it up this way. All right. So let's go back to the beginning. It says that the department, they estimate that 85% of cases brought to trial, the defendant is actually guilty. So we're going to put that 85% here. That means 15% are innocent. Now we're going to break up that 15%. We're going to break up that 85%. So how are we going to break that up? Well, some of those are going to be found guilty and found innocent. So let's see what it says in the next part of the paragraph. It says that, let me underline it here, 10% of guilty defendants are found innocent. Okay, so 10% of guilty defendants, that's what's actually happening, are found innocent. So that happens 10% of the time. That means 90% of the time, guilty defendants are found guilty. All right, and then it says 5% of innocent defendants are found guilty. So 5% of the time, they're innocent and they're found guilty. So that's 5% would go here. That means 95% of the time you're innocent and you're going to be found innocent, which is what you want. You want to have that happen. All right, so let's figure out what each of these values would be. So this one here, if you multiply those, you get 0.085, and this would be 0.765. And if we add those two numbers together, sure enough, we get 0.85. Let's look at these next cells. 0.95 times 0.15, this would be 0.1425. And this would be 0.0075. And again, if I add those two numbers together, I get 0.15. So now if we add our row totals, if we add the 0.085 and 0.1425, we get 0.2275. This would be 0.7725. Okay, so that's how you set up your table there. That's going to be worth the most points. And now we're going to have these two follow-up questions. So this next one, it says, what is the probability that a defendant who is found guilty is actually innocent? So out of those that are found guilty, that's that row. The total there, we have that total is 0.7725. So this is part B. So we'd have 0.7725 in our denominator. Our numerator is going to be the intersection of what we're looking for. So it says, what is the probability that a defendant who is found guilty, out of those that are found guilty, that they're actually innocent? So those that are innocent are these right here. Now that wasn't a good color to use because now I can't see that. But you can see here, let me do green instead maybe. There we go. So we can see there the intersection, what they have in common would be that 0.0075. So that's where they're innocent, but they're found guilty. So we're going to put that in the numerator. And when you divide those, we're going to end up getting 0.97%. Okay, now on your calculator you get 0.0097, but when you move the decimal to the left 2 places, you get 0.97%, or if you just rounded it to 1%, 0.97%, it's really close to 1%, you could do that too. Alright, so let's look at part C. So in part C, it's saying, what is the probability that a defendant who is found innocent? Okay, so this time we're looking at, whoops, out of those that were found innocent. So this time our denominator is going to be 0.2275. So out of those that are found innocent, what's the probability that they're actually guilty? So if we look at that first column here, that's where they're actually guilty. The intersection is a 0.085, so 0.085 goes in our numerator. And when you divide those out, let me just scroll down a little bit. When you divide those out, you get approximately 37.36%. So again, as a decimal, you'd get 0.3736. Just move it to the right 2 places to get your percent of 37.36%. So that's how you do number 8. So like I said, a lot of you guys had a question on that one. All right, let's look at 13 and 14 here. Both of these are very similar here. So they're both looking at this table. So suppose a student dormitory in a college shows the data in the table below. So here we have students that own a car and don't own a car, and broken down by freshmen, sophomores, juniors, and seniors. So to start out with, it says, estimate the probability that a student in the dormitory owns a car. So the probability that a student in the dormitory owns a car. So it means out of all the students, what's the probability that they own the car? So we're going to have to find a couple of totals here. Poof! And just like that, just like magic, we got our totals there. So I didn't want to waste your time by me plugging in those numbers. But you could have found those totals. That's going to be, we're going to need these to answer these questions. And so for number 13, again, it says, estimate the probability that a student in the dormitory owns a car. So if there is out of all of those that own a car, there's 290 that own a car out of 1,020 that are in the dormitory. So for 13, we would just take 290 divided by 1,020. And when you do that, you would get 28.4%. If you're wondering what do you round to, I'll make sure that I describe that on the test, so that way you know what to round to for each one of these. But then for number 14, when it says what percent of car owners are juniors? Okay, so now it's just talking about specifically car owners, not out of all those in the dormitory, just those that own a car. There's 290 students that own a car. So what percent of car owners are juniors? Well, there's 70 juniors that own a car. So it'd be 70 out of 290, which is approximately 24.1% or 24%. So that's how you do numbers 13 and 14 in the self-test. All right, looking at the review portion of the review. This one here, we got to. I'm going to make this table a little smaller so I can see it. But we're going to need some of those dice sheets, okay, to answer these questions. So for it says. So by the way, number 2. There wasn't a whole lot of people there's only just a small percentage of students that asked about number 2. So I'm hoping that those of you that had a question on number 2 by doing number 1 here will be easier, because there's about 30% of you guys that had a question on number 1. So it says in 1 and 2, so number 1, consider tossing a fair-sided die and subtracting the number on the first toss from the number on the second, resulting in a difference, D. Find each probability. So we're subtracting the first die minus the second one. We want to find the probability that the difference is less than 0. So when I look at this first column, all of these, because 1 minus 1 would be 0, so we want the probability to be less than 0. All of those other ones would be less than 0. 2 minus 2 is 0. 2 minus 1 would be 1, but all of these less than 2, or less than the pair of 2's there would be less than 0. These would all be less than 0. These would be less than 0. And that one would be less than 0. But all the other ones would be positives. So again, there's 36 different outcomes here. And out of those, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Whoops. We have 15 out of 36. Now, if I say on the test to write your answer as a fraction in lowest terms, which is what I probably do in this case, you'd want to reduce this. Okay, so that means we want to reduce it completely. So 3 goes into both of those to reduce to 5/12. That can't reduce any further, so we would just leave it as 5/12. Now for 5 through 7, so for 5 through 7 there was, I would say about 20 to 25% of students that asked questions on these. For these, it might be helpful to draw a tree diagram to make it easier to know all the possible outcomes. So when it says 3 fair coins are tossed, let's say this represents your first coin. The first coin you could get heads or tails. And then we're going to have a second coin, and we could get heads on the first coin, and then we could get heads or tails on the second coin. Or we could get tails on the first coin, and then we could get heads or tails on the second coin. And then we have a third coin, so it would branch out like this. So I could count up all of them on the bottom to see how many total possible outcomes there would be. Because if we look at this, we'd have heads, 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 tails. So in other words, 1, 2, 3, 4, 5, 6, 7, 8. There's a total of 8 possible outcomes. Okay, so for each of these, we're going to start out with our outcomes being out of 8. So now it says, what's the probability that we have all heads? Well, that only happens one way that we have all heads, so that would be 1 out of 8. So that'd be your answer for number 5. For number 6, probability of 2 heads. Now, for that one, we would have, let's see, let me erase this. So exactly 2 heads would be heads, heads, tails. We could get heads, tails, heads. We could get tails, heads, heads, and that's it, because tails, heads, tails. There's no other way to get 3 heads, so that we would have 3 out of 8 possibilities, and that can't be reduced. I would just leave that as 3/8. And number 7, the probability of getting at least 1 tail. So that means getting 1 tail or more than 1 tail. So we'll erase. There we go. There we go. All right. So I'm going to highlight all the ones that we have at least 1 tail. So we have heads, heads, tails, heads, tails, heads, heads, tails, tails. Okay, those all have at least 1 tail. So tails, heads, heads, tails, heads, tails, 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 heads, and tails, tails, tails. So if you notice, 7 out of these 8 had at least 1 tail. So we would say 7 out of 8 for that one. So that was number 7. All right, let's look at number 9. Tossing a fair die 230 times, what is the expected count of the outcome 3? Okay, now when we're dealing with expected counts, now this was not something that was really emphasized a whole lot. I think it was actually emphasized in a later section. I left it in the review because even though we did not talk about this, this is a good concept to be familiar with. Expected count just means what would we expect to have happen. Now when we roll a dice just one time, a fair dice, the probability of getting a 3 on just one dice would be 1 out of 6. Okay, so every time we roll a dice, we'd expect to get a 3. We have a 1 in 6 chance of getting a 3. Well, if we're going to roll a dice 230 times, well, now to figure out how many times you'd expect to get a 3 in those 230 tosses, we just take 1/6 of 230. And when you do that, you end up getting about 38.3 repeating. So we would just say approximately 38 times. I think your book did say 38.3 repeating. But that's how you would do number 9. So number 10, we would do the same thing. There's a lot more words here. So it says, according to a National Center for Health Statistics survey, about 4.7% of children between the ages of 5 and 17 missed 11 or more days of school because of illness or injury in the last year. What would be the expected count of students aged 5 to 17 in a school of 532 students to miss 11 or more days of school because of illness or injury? Well, we're just going to take that 4.7%, which has a decimal is 0.047, times the 532 students. Whoops. There we go. And when you do that, we get about 25 students. Okay, so that would be your answer for number 10. So again, to find that expected count, you just take the probability times the number of times it happens. All right, let's look at numbers 14 and 15. So number 14, now this is going to be a little bit different. If you looked at the answer key in the book uses permutations, which is fine. But if you're like me, if you're a visual learner, sometimes that's not as easy as just thinking about it logically. So how many 3-letter permutations? Okay, so 3 letters, so I'm going to have 3 blanks. Can be made from cabinet that start and end with a vowel. Okay, so let's look at how many vowels we have. We have 3 vowels to pick from. So we're going to start with, we would have 3 vowels to pick from. Now let's say one of those vowels gets, let's say the A gets picked. Well, we want it to start and end with the vowel. So now we would have 2 vowels to pick from at the end. So let's say if I pick the E. Now, that letter I that's left over is going to be put in with the other letters. So in the middle here, I would have 1, 2, 3, 4, 5 letters to pick from in the middle. Okay, 4 of those are consonants, 1 vowel. So we'd have 5 to pick from the middle. So we would just multiply those together. So we would just take 3 times 5 times 2. So 3 times 5 is 15 times 2 is 30. So for 14, you'd get 30. For number 15, if a coin is tossed 8 times, so 1, 2, 3, 4, 5, 6, 7, 8, we'd have 8 blanks here. How many possible outcomes are there? Well, if every time we flip a coin, there's 2 outcomes. You get a heads or tails. Heads or tails every single time. And so if we multiply those together, we would take 2 times 2 times 2 times 2, 8 times, or 2 to the 8th power. And if you did 2 to the 8th power on your calculator, you get 256. So there'd be 256 ways of that happening. All right, let's look at 24 through 27. 24, it says if A and B are 2 events where the probability of A is 0.6, the probability of A intersect B is 0.05, find the probability of B given A. Now, we want to make sure that you know this formula. The formula states that if we have the probability of B given A, we're going to put the intersection of those 2 events. By the way, it doesn't matter what order you put the letters in. The intersection of A and B and the intersection of B and A would be the exact same thing. And whatever you're given, so remember this, that line there represents the word given. So we say that we're probability of B given A. Whatever we're given, you put that in the denominator. So probability of A would go in the denominator. So now we're just going to put in what we know here. We know the probability of A intersect B is 0.05. We know that probability of A is 0.6. So we would just divide those 2 values, and you end up getting, for 24, you end up getting 0.083. 0.083 repeating, or we could say 8.3%. All right, let's look at number 26 now. By the way, if you notice that the buzzing in the background stopped, I apologize. I just realized that I had my heater on in the room because I'm in a freezing cold basement. I'm not at school today, and our basement is kind of chilly. And so I had my heater running and just got to thinking, oh, I wonder if the speaker is picking that up. And I checked, and sure enough, it was faintly, and so I stopped it, but I'm not going to go back and re-record. So I apologize for that if you were listening and had that frustration. But anyhow, let's look at 26. So 26, it says the probability of A is 0.6 and probability of B is 0.7. Explain why A and B cannot be mutually exclusive. Now remember, to be mutually exclusive, that means there can't be overlap. Well, when we're dealing with percents, it's fine to be working with percents, but one way to tell if there's overlap or not is if the 2 probabilities add together to be greater than 1, that means there has to be overlap. Okay? Now the probability, since if you add 0.6 and 0.7, you get 1.3. Okay, so 1.3 is bigger than 1, so there has to be overlap by at least 0.3 or 30%. So that's how you can tell that they are not mutually exclusive. Now, if just because they add up less than 1 also does not mean that they're mutually exclusive, because just to show you, we could have a scenario like this where maybe you have 0.4, let's say, is in A, and let's say in B we have 0.3, and there's an overlap of 0.05. And so that means over here in just B we'd have 0.25, over here in just A we'd have 0.35. So again, if you were to add those together, we end up getting an answer less than 1. But there's an intersection because that means that there's another event or a probability that's outside of the Venn diagram. So I don't want you to think that just because they add up to be less than 1, that it also means that they're going to be mutually exclusive, because that doesn't mean the case either. It's just that if they add up to be more than 1, you 100% know there's got to be overlap. All right, 27. So for that one, as far as what to write down, there's not a whole lot. It's just more important that you understand that concept. For 27, A and B are two mutually exclusive events, where the probability of A is 0.25 and the probability of B is 0.3. We want to find the probability of not A or B. Okay, so these are mutually exclusive, so there's no overlap. So the probability of A, or probability not A or B. So the first thing we need to do, because to figure this out, it's going to be 1 minus the probability of A or B. Okay, so the first thing I got to do is figure out, well, what's the probability of A or B? Now, the fact that they told us they are two mutually exclusive events means that there's not overlap. Whoops. So that means to find the probability of A or B, I would just add these two together. There's no intersection to subtract. And so if you subtract those, or if you add those two together, 0.25 plus 0.3, we get 0.55. So probability of A or B is 0.55. So probability that it's not A or B means that we would take 1 minus 0.55, which gives you 0.45. So that's how you would do number 27. All right, let's look at 29. So 29 and 31, actually, these are both ones dealing with whether or not they're independent. So remember, to tell if they're independent, here's what we got to show. We got to show that the probability of event A times the probability of event B, whatever those two events are, multiply those together. We need to prove that they're equal to the intersection of A and B happening at the same time. So for number 29, it's meant to be real simple because they give us all the pieces we need. So if we take 0.4 times 0.25, we need to see, do they equal the intersection of A and B? Do they equal 0.1? So if you're to multiply those two numbers together, if we take 0.4 times 0.25, sure enough, we get 0.1. And it equals 0.1, so they are independent. Now, if they gave us a number bigger than 0.1 or smaller than 0.1, or if we got a false statement where if that had happened, then we would say that they are dependent. But for this one, they're the same, so it's independent. Let's look at number 31. Again, we're going to need one of these dice problems, or one of these dice sheets here. So I'm just going to make this a little smaller so we can read it all at one spot here. Okay, so as a fair six-sided die is tossed twice. Okay, so in other words, we have our two dice. We'll just say the first number represents the first toss, the second number represents the second toss. So we want to find, so event A is the first toss is a 5. Event B is the sum of the tosses is 7. All right, well, let's start with the first dice is 5. Okay, so we want to find these. I'm just going to write this out. So event A is the first toss is a 5. So that happens 6 times out of 36. Now for these, we want to reduce these. And the reason why we want to reduce them is we're not adding, we're multiplying. When we're multiplying, we don't need to have common denominators. So to have to do less reducing in the end, it's easier to reduce at the beginning. So 6 over 36 reduces to 1/6. Okay, event B is where the sum of the tosses is 7. So here is where we have the sum of the tosses is 7. So that happens 1, 2, 3, 4, 5, 6 times is there as well. Whoops. And 6 over 36 reduces to 1/6. So if we multiply those two together, we get 1 out of 36. Now we want to see, does that equal the intersection of A and B? Well, if you notice, the intersection of A and B is right here, because that's where the first die is a 5 and the sum was 7. It's the only time that's going to happen. So that happens 1 time out of 36, and since those two are equal to each other, they in fact are independent. All right, let's look at number 36 here. It says, consider the experiment of flipping a coin, then rolling a die. So we want to write, first off, we want to write the sample space. So to help me write the sample space here to make sure that I don't miss any, I'm going to draw a tree diagram. Okay, so we have two events. Flipping a coin. So in our first event here, flipping a coin, we could have two possible outcomes, heads or tails. Then the second event is rolling a die. Now when you roll a die, we could get numbers 1 through 6. Or we could have gotten tails first, and then we could have rolled the die and gotten 1 through 6. Alright, so I'm not going to list them all out, but here's how you could do that. You could say, you could get heads 1, heads 2, heads 3, heads 4, heads 5, heads 6, and then the same thing for tails. Tails 1, tails 2, tails 3, tails 4, tails 5, tails 6. Part B says list the outcomes in the event the coin shows heads or the die shows a non-prime even number. So now you might not have known what that last part was, but let's start out with all the times where we get so it says the coin shows heads or the die shows a non-prime even number. So heads would be all of these. Okay, so showing heads, we would have heads 1, heads 2. I'm not going to write these all out, but we'd keep listing them all the way until head 6. Okay, so we would have 6 outcomes there. Now we also got to look at or, so if it's not heads or a non-prime, or the die shows a non-prime even number. So the prime numbers are 1, or 1's not prime or composite, but it's not even either. 2 is our only even number that's also prime. But 4 is not a non-prime, so we want to keep that. All right, but the 3 is prime, so we're going to cross that out. 5 is prime. So the only ones that are non-prime even numbers would be the 4 and 6. So we could get a T in 4 and a T in 6. So those would be all the possible outcomes. I guess I could have just written the H4, H5 there because there's just 2 extra letters. There. Now we've got them all listed. All right, so let's, letter C. How many outcomes are in the event the die shows a number less than 3? So now it doesn't matter what's on the coin as long as the die shows a number less than 3. So we could have heads 1, heads 2, or tails 1 and tails 2. So there's 4 outcomes where that happens. All right. So 40 and 41 here. This was actually a tricky problem if you didn't understand this table or if you just looked at it quickly. Because here it says a city recently opened a new park and planted many new trees of 3 different species. Shortly thereafter, a storm knocked over some of the trees. This contingency table gives a count of trees planted and knocked down by species. So we already have the trees planted represents a total. Okay, so and we could add all those 3 together, which we might need to do here in a minute. But that would give us a total number of trees. And out of those trees, 16 of them were knocked down that were maple, 8 that were knocked down that were oak, and 17 that were knocked down that were ash. And like I said, let's just go ahead and add those 3 numbers together. 102, 68, and 85 add up to be 255. So that means there's a total of 255 trees that were planted. Okay, so we might need that because here it says 40. What percentage of each species was knocked down in the storm and which species seemed to be the sturdiest? All right, let's start out with the maple. So there were 102 maples planted, 16 of them were knocked down. So we would just do 16 divided by 102. When you do that, we get about 15.7%. Then let's look at the oak. The oak trees, there were 8 that were knocked down out of 68 that were planted. And 8 divided by 68, that's about 11.8%. And the ash trees are a cheaper tree, but you'll see why here in a second. And they grow quickly, but they're also prone to be knocked over because they don't have as good of a root system because they grow so quickly. And so an ash tree, there's 85 that were planted and 17 that were knocked down. So that gives you a total of 20% of those trees were knocked over. So when it says which species seems to be the sturdiest, it looks like the oak because those had the smallest percent of trees that were knocked down. And then in 41, it says, what percentage of the total trees were oaks before the storm? Okay, so out of the trees before the storm, there were 68 oak trees out of 255 that were planted. So this is for 41 here. So we would have 68 divided by 255. And when you do that, you get about 26.7%. So about 26.7% of all the trees that were planted were oak trees. Now, the second part of 41, what percentage are oaks after the storm? Okay, well, we know that there was 8 trees knocked down during the storm, so that means that there was 60 trees that were left over after the storm. Now, we need to figure out our total trees that were knocked down, so we can figure out what total were left over. So 16 plus 8 plus 17 tells us that there was 41 trees that were knocked down. So that means after the storm, if I take this time, this is going to be a unique total because there's 255 trees before the storm, 41 trees knocked over during the storm. So that means after the storm, if we subtract those, we get that there's 214 trees left over after the storm. And out of those trees, 60 of them were oaks. So we would have 60 out of 214, which when you do that, I don't know why that's selecting, but 60 divided by 214 would give you your answer, which is about 28%. So after the storm, there's pretty close to being about the same, if not just a little bit more percentage of trees left over that were oaks after than before. All right, so for number 43 here, it says, what is the probability of guessing correctly on exactly 4 of 5 multiple choice questions with 4 options each? Oh, actually, you know what? I remember why I included this one on here. This was one that slipped past me. I didn't read that carefully enough. The book accidentally put this problem in this review. It actually pertains to something we're going to talk about in the next chapter, which is actually going to be, ironically, chapter 10. So they made the mistake of putting something from chapter 10 into chapter 6. There is a way to do it with what we've done in this chapter, but it's a lot harder. This is a super simple problem with something that we're going to learn about in the next chapter. So I apologize for that slipping past. But number 44 is kind of similar. That's why I thought that these two went together. But what is the probability of 4 consecutive days without rain if the probability of rain on any particular day is 0.3, regardless of whether it rained the previous days? All right, so we're going to have 4 days, 4 consecutive days without rain. Now, the probability of rain is 0.3, so that means we have a 70% chance. So if we have a 30% chance of rain, that means we have a 70% chance of no rain on each day. So we'd have 0.7 times 0.7 times 0.7, or 0.7 to the 4th power. And if you do that, you get 0.2401. Or we could say 24% if we wanted to write it as a percent. But that's how you do number 44. All right, number 50. Philip has 5 high school subjects and he has 8 different colored folders. Okay, so 5 subjects, 8 colored folders to pick from. How many ways are there for him to file his papers by subject in different folders? Okay, so this one here, this is a tricky problem. The fact that it says that we're going to organize it by subjects, let's go back to the beginning. There's 5 subjects. Okay, and in those 5 subjects, we have a total of 8 different colored folders. Now, once you pick a color, you're not going to be able to reuse that same folder. So there's 8 different colors to choose from for his first subject, and then 7 colors that he'd have to pick from for his second, then 6, then 5, then 4. So we multiply all those together. When you do that, you get 6,720 different ways for those subjects to be arranged into folders. So then in part B, it says, how many ways are there for Philip to order his 5 subject folders? Okay, so now this doesn't matter what color they are. It's just that he has 5 subject folders. And let's say it's math, science, English, social studies, and art. Okay, so there's 5 to pick from. It doesn't matter what color. So once he picks one of the classes, or he'd had 5 to pick from for the first class, if he was going to put that first in his bag or wherever he was going to put it on his desk, he'd have 5 to pick from to pick first. And then once he picks one of those, he would only have 4 subjects to pick from for his next folder in the pile. and then 3, then 2, then 1. So you multiply 5 times 4 times 3 times 2 times 1, and when you do that, you get, for part B, you get 120 different ways for that to happen. Now, using your answers for part A and B, how many total possibilities does Philip have for organizing his papers considering both order and folder color? So for this one, what we're going to do is we're just going to multiply, because this, again, ties into something that, well, I guess we have talked about this. So we're looking at probability of arranging them by color and subject. So we're going to multiply those two numbers together. So we're just going to take 6,720 times 120. Okay, it'd kind of be like if you're comparing this to a simpler example would be like when we did like if you're going to a restaurant and you have 3 different main dishes to pick from and 2 different desserts. You want to figure out how many different ways there would be to arrange those. Well, we just take 3 times 2 and get 6. It's just that here we have much bigger numbers that we're working with. We have 6,720 different ways that we could arrange them by the subject by the different colors of folders, and then 120 different ways that we could arrange them by subject. So we want to figure out what's the probability, or what's all the different arrangements that we could have with both order and folder color. So we would multiply those. So a hint is when we see the word "and" when we're dealing with probability, usually means we're going to multiply. So we multiply those two together. And when you do that, you get a big number of 806,400. That would be your answer for part C. So that's it. So that is your review. So hopefully you were able to watch the ones or all of this that you needed. And this will be a useful tool for you as you review for the test.